So we ended last time looking at these curves. So let's look at, and we asked the question: what would the red curve and the blue curve on the position time plot? What would they mean? The red curve is positions going down with time, and that all that means is we have an object that is moving to the left, and so we have an object moving to the left. Sorry, that should be red. So an object moving to the left, and eventually it crosses, the 0 point, kind of keeps going. The 0 point is pretty much arbitrary. Now the other one, this curve here, what we have is we have something that starts off rather slow, and we can tell because essentially, the slope of the line here is pretty slow, is low, and then as time goes on, the slope itself changes. So this object is speeding up and speeding up. So it's an object that's moving to the right, and then gets faster and faster as it goes along. Now, when we're dealing with things that change in speed, we are interested in understanding, where things are, and it helps make two types of plots. So you have the position and time, and then we're going to look at a speed and time, where speed might be changing. I'm going to move this down a little bit. Okay. Now, in the prior example, we had speed that was constant, so we had speed at 2 meters per second, and it was constant, so we can draw this. And we were starting, let me erase these lines here, and we were starting at a position of x was 3, and in 1 second we moved up 2, and another one we moved up 2, and so we followed this track here. Now, what we're often interested in is what is the position at some specified time later on. So I'll call that the final position, and so what I'll have is I'll have the final position. Okay. And we could use the kind of y equals mx plus b form, so mx plus b form for a line to figure this out. And in which case we have the final position, which is, at some point up here. What is the final position at some given time? So x is time here, and the y equals mx plus b, and the b is the intercept, so that's actually the initial position. So we have the initial position plus m, which is the slope, which we already found out that's the kind of rise over run, and that's given actually by the speed, and then we have times time. Okay, so, and I may abbreviate this as, final position xf is equal to initial position x0 plus speed times time. Okay, so that's just an abbreviation of that. And again, we're just using the equation for the line. Now, there's another, actually somewhat more useful version of this, and that is at some given time, if I look at the velocity or the speed and time plot. Velocity I'm going to be using as speed, just velocity is a speed with direction, but since everything here is one directional, they're identical. So I have a speed and time plot, and I have this area here, and it turns out that the equation for the final position of something from the speed and time plot, we have the final position again is equal to the initial position plus the area under the speed curve. All right, so in that case, it's actually this rectangle, and then as you can see, the time we're talking about here, time, and that's the width of the rectangle. The height of the rectangle is just the initial speed in this case, which is, since the constant, it's the same thing, and so what we have for this case is we have the final position is equal to initial position plus the speed of the object times time, and we get the same equation. But let's look at a case where the speed is changing, and so what we have is the following. So let's imagine we have. I'm just going to do a couple points so I can get the line. let's imagine we have something like this, and then so now we have the speed is actually changing in time, and again, because it's a line, we have a slope for this, so we looks like we can do something like this: a rise over run. It does 2 meters per second in 2 seconds, so the slope here is 1 meter per second over a second. Kind of a funny unit, but we'll deal with that. I'm going to give this slope a name. I'm just going to call it A. It's the name is the acceleration. I don't think that's particularly important to do that, because this is only going to work in a case where the speed is increasing constantly, which is not it's somewhat common, but there are a lot of exceptions to it. Okay, so now if I want to do the final position, I look at it's again the initial position plus the area under the curve. And what is that? What is that area? Well, that area is really just this area here plus the rectangle. So it's really this entire funny little shape, which we can kind of break it up however we want to. That's convenient. And so what we have now is we'll have the final position. Let's call it xf. Okay, is equal to the initial position x plus the area under the curve. So we're going to do the rectangle first, which we already figured out, and that is simply the base times the height. That's a rectangle. So we have the base is time, and the height is the initial speed. Plus the area of this rectangle, which is 1/2 the base times the height. So it's 1/2 the base, which is again time, and then the height, which is the final speed minus the initial speed. That's because this here is the final speed that we're looking at, and here is the initial speed. Finally, I want to show that this equation, I'm going to move it up a little bit, can be rewritten in a somewhat different way, because I see I have initial speed there and I have an initial speed there, and you'll notice that that this is equivalent to x naught plus time times vf plus v naught over 2. Okay, now what all I've done is I've taken one full v naught v0 and subtracted off a half of a v naught, and so I get a half of a positive half of a v naught, and that's what I got here, and I have a positive half of a vf right here. So this is all I'm doing, and what all this is, which is interesting, is this is time plus the average speed. So we can think of this now, and again, this is only in the case where the speed is changing in a constant fashion, and then we get this equation. And what in fact we get for position and time is a parabola, and it'll actually look something like this in position and time.